Sorry for the technical difficulties. I'm the person, I think, between you and lunch. I apologize. Don't take it out on me. I'll try to be quick. So we have been working for the past year. I've been working with the 3 freshmen. They were freshmen, who were the first 3 authors, and a few other people on getting CFE running on an OSAL based on a microkernel. And I want to present the work that we've done here and give you some context behind it, and more importantly, understand whether any of this is interesting to you all, and if some aspect is interesting, which part we should keep pushing on. I'm at GW, so I'm not that far away. I think this is something that I don't need to say. Traditional satellites, they work in a certain way. CubeSats change the game. They often can have commodity processors that can be faster. They often have multiple cores. But unfortunately, they don't have much software fault tolerance. If you don't have much hardware fault tolerance, you don't have hardened processors, these types of things. So we were asking, if we have CubeSats, we have these commodity processors, what can we do with that to actually have some degree of fault tolerance? And of course, the obvious thing is we have a little bit of spare capacity in the hardware. We don't have hardware reliability. So can we use that to provide some degree of software reliability? And additionally, how can we most effectively use the parallelism? I'm waiting for the 6.6 release so that I can start looking at the SMP support in that, but you'll see what I'm looking at is slightly different than that anyway. So this is the first question that I'm going to try to give some context for how we are looking at it. How can we use the extra computational capacity of these systems to increase fault tolerance? You just heard that we have FreeRTOS and CFE running on a system with 2 megs of RAM, so perhaps talking about spare capacity is a little bit not appropriate, but certainly many of these types of chips do have it. So from a software fault tolerance perspective, we kind of look at 3 different things. We say, can we detect faults? If we can detect faults, we can do something about them. If we can do something about them, we want them to impact a minimal subset of the system so that we can do something about that minimal subset. So how do we control the propagation of those faults? Once we've controlled the propagation, how do we go into some sort of a remediation mode where we can say, there was a fault, let's do something about it and get the system back into a functional state. So this is how we think about the system, and I'm going to be focusing to start on this middle bullet because I see it as rather fundamental. I think most people in here by now have seen some sort of a diagram. Now I have a different representation. It doesn't have Mario jumping around, so it's significantly less interesting, but it has circles. I'm an operating systems professor. I draw circles all the time. We have our mission-specific applications, the general utility applications provided by CFE, CFS. We have the different features within the core flight executive, and then we have different parts of an OSAL. And a lot of the use of CFE that I've been exposed to, I'm sure there's a lot more that I have not, looks at all of these in a single fault domain and a single protection domain. Throughout the slides, I'm going to have this dotted line as some notion of a protection domain. The problem with that is, of course, from a software fault tolerance perspective, if you have a fault in one place, that can trivially propagate throughout the system. You can have a mem set that can go crazy, overwrite a lot of memory, and propagate the fault. It becomes difficult to say what your properties are with respect to the fault tolerance of the system. Some of the OSAL layers that we've looked at do provide some form of a separation. So the prototype here is the Linux OSAL. Of course, the Linux kernel itself is isolated from any of the bugs above. But the problem with using something that supports full POSIX in some environments is that full POSIX comes with a lot. And when you start talking about software fault tolerance, you start talking about what is the memory footprint, what's the cache footprint, and what's the CPU footprint of these things. And if you look at something like Linux, that ends up being relatively large. And if you start putting that as the OSAL or as the operating system implementation, and you have a fault within that, it of course trivially propagates throughout the system. So a question, it's not necessarily, there isn't really a correct general answer, but a question is, how can we get software fault tolerance when we have a relatively small amount of code up top for our missions and a relatively large amount below. So what we decided to look at is a different version of how you might configure the system, which is adding a lot of fault protection domains, so that if you have a bug in one of these small little pieces, it will not necessarily impact the rest of the system. Note that I've kept this picture relatively uniform, except at the bottom here, well, there's a little bit of configurability for whether you actually, might want everything in the same protection domain or not. So we have a research operating system that we've been developing for over a decade called Composite. It's relatively small. It's about 7,000 lines of code, and it focuses on real-time and embedded systems. It scales relatively well from very small systems to very large. We support virtualization for small microcontrollers, and we can run 8 FreeRTOS instances within about 512 kilobytes of memory, all the way up to 40 core machines where we can achieve significant scalability gains. It's focused on using IPC between protection domains. For anybody who knows what a microkernel is, this is just kind of the typical definition. Break up the system into small chunks and communicate between them to achieve the functionality that you require from the system. It's based on this idea of being able to move a lot of the resource management policies within what would traditionally be in the kernel up into user level, so that now they can be isolated and fail independently. We've done this for a large number of components. There is no scheduler in the kernel, which is a very strange thing to hear, but that's implemented in a user level component along with file systems, networking, device drivers, et cetera, et cetera. So this allows us to have a relatively small body of code with a small footprint on chip in cache that could fail, that if it were to fail, the entire system goes down, and move the rest into user level and try to recover that instead. So we, over the past year, have been trying to provide an OSAL layer within this system for cFS. And this ends up looking a lot like a combination of the two diagrams that I had before. We're now removing the applications and the different applications within CFE into separate isolated protection domains that all communicate with what is traditionally the CFE, that is now still a user level component, and different components within the system that provide increased functionality. And if you look at this mess of arrows at the bottom, I kind of intentionally want it to look like a mess because that traditionally is overhead. You are not getting this stuff for free. So this system is designed fundamentally to try to make that as efficient as possible. So our IPC between separate components is round about the same overhead as a system call in Linux. So it's not free, but it's relatively manageable if you want that increased fault tolerance. Our OSAL supports fixed priority preemptive scheduling, round robin within each priority inheritance for locks, all the typical things that you'd require for a real-time operating system. It includes a RAM-based OS. We decided that we wanted to keep things simple to start, so used a RAM-based FS for that. Our loader is somewhat immature, but it's able to load applications both within the same protection domain as a traditional loader would, or across two protection domains. This is how you actually boot up different applications. The dynamic loading has been hooked into to enable that. And we have one component currently that supports all of the cFS core and a lot of the operating system stuff that you may require. The OSAL implementation itself is about 4,000 lines of code. The OSAL unit tests are not completely successful, but we're getting there. Usually where we're failing is just because we said, well, I'm not sure if we really need to implement that. I'm not sure if people are really using it. And then we find out some of the applications do, and we say, okay, we'll fix that then. There are a large swathe of unit tests that we don't actually even plan on supporting because they don't make sense. The OS call failure ones, if you're familiar with them. What we're currently doing is we don't support all applications because they need to communicate with the CFE. They need to make what we would traditionally think of as function calls to the CFE core. Instead, now we're making IPC calls to To pass arguments, you need to serialize and deserialize data, and we just need to write the wrappers for all of that or programmatically generate that. So that's one of the main things that we're working on now. So this is what we've been doing and kind of where we're at. I want to give some view of what we've done in the past in terms of research for using composite for fault tolerance and for parallelism, just to give you an idea of the areas that we could dive into with this type of a system. Again, I want your feedback on kind of what's most useful and interesting. So I'm going to be focusing on these two other pieces, detection and remediation. And at the bottom of a lot of these slides, you can see I'm saying whether a technique is useful for detection, whether it's useful for returning the system into a known state. I thought I'd start with something that I think everybody is familiar with because it's just kind of the industry standard for how you actually build fault-tolerant systems, one of the bases for that, which is just watchdog timers. All of your applications and systems periodically say, I'm in a good state. The watchdog timer comes along, says, has everybody said you're in a good state, yes or no? If so, you keep on trucking. If not, you reboot the system. So detection is explicitly managed by the applications, and reboot is kind of the remediation mechanism. We don't do anything special here. I think it's just interesting to point out the de facto. People have talked a little bit today about voting, and that is a typical way that we think about adding some form of reliability. So adding redundant computation, possibly multiple CPUs, multiple pieces of hardware, and voting on the output. That's fine. As it stands, if you're doing it with multiple pieces of hardware, then you have the overhead of needing multiple pieces of hardware there. You need to have at least multiple cores, but likely multiple actual boards. If you want to do this in software, then you can, on the left, break up the system and say, I'm going to be voting on the input and output of my entire CFE body and deciding whether two redundant executions agree. 3 redundant executions if you want to have some remediation and not just detect errors. However, what we've been working on more recently is the far right, which is breaking up subsets of the system so that you can have a failure in a subset of it and have remediation on that rather than for the whole system. Our voter is somewhat in progress. It's less than 800 lines of Rust right now. We're using Rust just because it's a programming language that enables us to have a little bit more confidence in what we're doing. And this heavily utilizes the efficient IPC support by our kernel to be able to enable the voter to interpose on all the operations that different components want to perform. Checkpoint restore is a typical way that you do fault tolerance, not necessarily in the domains that we're used to, but in, for instance, the cloud domain. You are typically just taking a snapshot of the system over time as it executes, usually periodically. And if you find that there's some sort of a failed state, then you restore from the most recent checkpoint. I have a natural aversion to checkpointing in real-time systems because you're checkpointing, and that checkpoint is for a time in the past by definition. If you fail and restore that, then your software thinks it's in the past, but your satellite has gone 100 meters into the future. So that's complicated to get working in real-time systems, but if your checkpoint latency is low enough, then it might be feasible for some systems. We've compared in Composite our support for checkpointing versus in Linux user-level checkpointing and in Zen, which is apples oranges. And we can get it relatively efficiently down to essentially the cost of a mem copy because we very intentionally lay out everything in memory. Whereas a lot of these other techniques are more general purpose, so they cannot. Our point here is this helps a little bit with being able to adopt this within real-time systems. We've come up with another technique that we call the computational crash cart. It's like a crash cart when somebody's heart's failing, you zap them with electricity. This is the zaps to a component when it fails to try to resuscitate it. And I'm not going to go over it really at all here, but the idea is that some system-level components, things like schedulers, things like the CFE, we can actually have them fail and recover them within a very, very small amount of time by using a semantically aware technique that kind of understands the communication that happens between different components. This has a focus of working for real-time systems, fundamentally. And then the question is, so that supports resuscitation. If you have some sort of a fault, what do you do? Same with checkpointing. But the question is, how do you know that a fault has happened? If you have a fail-stop system or a fail-stop fault, then that means that you've done something that you can detect. There might be some sort of a page fault or whatnot. But that's often not sufficient. You can have latent faults that do not demonstrate themselves immediately. So we've created a couple of systems where we monitor the interactions between different portions of the system, the communication between different portions of the system, and check over time whether that adheres to the model of the system. The model in this case, we use a real-time model to describe the timing properties of the system. We've also used statistical models and machine learning techniques like clustering and sequence learning to do the same for less stringent systems. But I think less appropriate for this context. The second question that we wanted to ask is how can we use the parallelism within our system to help out the CFE in some way? And I'm not going to go into this in much detail, but our kernel is entirely lockless. It is programmed to have all of its operations be weight-free. So we have a lot of experience on lock-free and weight-free algorithms. What that allows is as you add cores to the system, the timing properties of your kernel don't necessarily change. So from a real-time perspective, this is appealing. Because of the focus on IPC within the system, we are thinking that CFE and cFS, you do use locks a lot. They are a great abstraction for many things. That limits scalability, especially on real-time systems. So having the ability to actually break up applications, not just the CFE across different cores, and use inter-core communication for some of those might be an interesting direction and one that we support well. This is not the same, but it gives you some indication of the usefulness of the system. We've implemented an OpenMP runtime, which is a parallelism programming model for fork-join parallelism in Composite. And our latency for being able to create a whole bunch of threads on different cores and then join them back together in the worst case for real-time systems is 2 to 40 times faster than Linux. It's a little bit of an apples-oranges comparison. But so I've been talking about CFE and our OSAL version for Composite. I talked about fault tolerance and parallelism. And my big question here is any of this useful to you? And is any of it interesting? And what direction should we go with it? I am leaving at 2:30 because I have to go run my own conference in Paris. But I will be here before 2:30. So please seek me out and give me your opinion. Even if your opinion is, this is all crap, why would you do this in this domain? Whatever it is, I want to hear it because I don't have the context that you have. All right, any questions or comments?
I have 2 questions. One, you said that your kernel is primarily lock-free. Is that because everything just goes through a single pipe IPC receptor? So since an IPC message can only be delivered one at a time, they're funneled in order. Is that how you basically are lock-free?
I'm not going to be able to satisfy your question in the time that I have up here. The high-level idea is we actually do not queue messages within the kernel. Instead, the kernel is in charge largely of control flow transfer. The data structures within the kernel are uniformly represented by radix trees, and we've made sure to implement those radix trees in a weight-free way. So the semantics around actually passing messages, usually shared memory and orchestrated by user level and management components. Yeah. Good question, though.
And my other question, is anyone? All right, so my other question, you had a table up there where you said you were comparing the IPC mechanism to the Linux system calls, and you said approximately 600 cycles for system call, 700 for IPC. And I'm just curious, to me, that sounds like an apples to oranges comparison. I'm wondering how was this what you're calling 600 cycles for system call measured? Like, you know, what was the mechanism for that?
So that was,
the methodology?
if I remember correctly, that was a version of get time of day that was orchestrated to not go through the vsyscall page.
So then you're trying to compare something like let's take it from the microkernel point of view with the message passing. So you're saying I'm going to send a message and then I'm going to get a response back, just as if I were to make a system call and have a return value.
Correct. So it's a two-way IPC. It is kind of calling to something and then getting a response.
Yeah, I'm just I guess I kind of doubt those metrics because I mean the system call is essentially, you know, it's basically some type of soft interrupt on most platforms. You just change privilege levels. Sometimes there's a context save and restore. You're talking about serializing data across a memory space. So you're going to have to do some type of address translation, whether the MMU is already set up or not, and then deserialize, plus you're waiting for the response. And so you're basically doing at least 2 thread dispatches in that case. I would argue that I would think that would be significantly slower than a standard system call, not just on the
And I think that's a
15%.
fair intuition. But since 1993, there's kind of a lot of documentation on how to implement microkernels in a way that you get away from a lot of the overheads that you'd expect. And I mean, my intuition matched yours, to be honest.
Okay.
I was really surprised when we were doing the metrics for Linux and found out that, I mean, there's just more involved in doing a system call in something like Linux than I would have expected. And what you really want to, so these are, full disclosure, I mean, these are on Intel machines, x86 machines, so they're heavily out of order, they're heavily optimized, whatever. And the thing that you typically do when you want to optimize these systems is optimize for memory accesses. And our memory layout is done in such a way that we have max 2 TLB misses, max 8 data cache line accesses for every single one of these things. Linux, I mean, these data structures are just more spread out. So my intuition matched yours until we measured it and kind of dived in.
So is this, I guess I'll ask one more. Just brief, I mean, so I'm not asking this question to criticize you. I'm asking because I'm actually interested in how the IPC was implemented in such a way that you could get that kind of performance in comparison. Is that something that we can look at, or is it all closed source?
Geez. Oh, no, this is all on GitHub. I'm an academic. I'm not trying to sell something. There are a whole bunch of papers. You can read the papers. I apologize. Probably should have flipped to that side. And please feel free to email me. I would be more than happy to provide context on all of this. This is probably the one that you are most interested in, right? Given this discussion. What's that? The second to last one talks about we're on the 3rd version of the kernel. That talks about this version, yes.
So I don't know if you saw actually Lori's slide touched on it, that I developed a voting application we have a set of model-based diagnostic engines that we ran in the real-time multi-CPU environment. So you and I should touch base briefly to talk about that, and if that makes any sense. I mean, this is a different layer that the brain's still hurting, so once it stops hurting, maybe I'll understand how this fits together, but I think there's something.
Now you know how I feel for the rest of this, so we can bang our heads, make them hurt more, and then knowledge comes out.
How do you deal with issues that could arise in the voter itself as far as faults?
So when you have a voting-based infrastructure, the voter is a single point of failure typically. You only have, as far as I know, 2 recourses, and there may be more clever people than me, but the first is keep it simple and keep it small footprint, both in time and space, and the second is use compiler techniques to help you out, add redundancy into the code and whatnot to sometimes mitigate the effect of SEUs. Okay. But if you are more clever than me, then I'm all about it.
I'm just curious, when you've looked at this, how you've implemented voters. I mean, there's a number of different ways and a number of different policies that I know that others have done. I'm just curious to see what you've done, or whether or not you've looked at problems that could arrive with the voter itself.
I've looked at some, probably not all. So okay. I'd love to hear more.
Okay.
I have one more
Now it's
I
Steve.
want to be clear, he's keeping
It's
you
Steve
from lunch,
between
not
right.
me.
That's what I was.
I can ask you just one more. But you,
I was
so a
joking.
lot of what you, it sounds like a lot of how you get the optimizations that you talk about have to do with taking the time to tune your memory layout. And of course, a lot of people do that even on bigger systems like running Linux or Windows, where you play with memory layout to get cache.
Oh, yeah.
As you mentioned, do you have any tools or methods that assist in that with this environment, or is it just kind of the standard stuff that people do in the larger systems?
I wish we did. That work would to some degree make me obsolete, because this is one thing that I know very well and have trained myself in very well. I don't know a way to automate that. Thank you all.
All right. Thank you, Gabe.